Alright guys, good morning. I guess you're going to receive your midterm grades by the end of the weekend. And then you have a couple of more days after that to drop the course if you want. Alright, so we're almost done with the density estimation part. So today, at the last part, I'm going to just sort of have a recap on the whole distribution and the Gaussian models. And then we've already been seeing the hard version of the EM algorithm. Now we're going to conclude the whole section with the soft version of that. So you recall we started with the univariate Gaussian distribution. So in 1D, so here are a bunch of examples. Each of them has their own mean and variance, so mu and sigma square. And if you recall again, on a normal distribution or a Gaussian distribution, normally mean. So I'm talking about this one, the red here. So normally the mean will be the maximum point here. So that would be the mean. And it's equal to 0, right? In this case, on the green line, so you have your mu minus 2. That's why minus 2 has the highest value. And also we talked about the variance in a normal distribution. So since we calculate the variance or sigma by each of the x's minus their mu, right? So suppose your x's are here or here or here, and mu is in the middle, the highest point. So what you see here is always sigma, right? The same here, another sigma. And that's why normally we refer to this window by 2 sigmas. And also the 68% confidence level and 95% confidence level can be calculated easily in a normal distribution. You don't need to know that. These are for other tests that we might use. So you see, using a Gaussian distribution or a normal distribution is going to be beneficial in many ways. We have a good estimation of the data. We have a good estimation of the distribution, and we can use these parameters in order to fit several data points without knowing their labels, right? And that's why we use Gaussian models, GMMs, as a very powerful mean to do unsupervised learning for clustering methods. So again, we can define them by a normal distribution represented by n for x's. So x is scalar here, so mean and standard deviation, or the variance. And we talked about the probability that this gives us. We talked about this as a normalizing constant. And then that's an exponential of a quadratic function. And that's going to give you an estimate of your true probability, right? So now, can anyone tell me what's the difference between these two with the hats as the estimate and the real mean and variance? So these two are maximum likelihood estimates, right? The estimates for mean, the estimate for the variance. So what's the difference between these two and this mean and this variance without the hats?
Is it the normalization?
Normalization, no. So let me recap another thing. So when you have several data right here, and you have a estimate of the distribution. So this estimate is your best fit model using any models. In this case, we use Gaussian models to come up with this bump-shaped function, right, for an estimate. So that's why I'm drawing it in dashed lines. The real Gaussian distribution, the real one, could have been this, right, or this. So that was the real one. That was a true case with its own mu sigma squared, right? But this one is your estimate, given your data. You sample from your data, and you found an estimate using this. So these are having had as estimates, right? And the probability as well. So sometimes in statistics, we call this empirical data because these are the ones that you experimented with, right? I'm not sure we can read this. So yeah, these are called empirical data. And these two mean and variance in this case represents, depending on the samples you had, depending on the number of empirical data you had, which was n, you're going to come up with an estimate of a mu for this distribution and this, and an estimate for your variance, right? Is it clear now? All right, so that was a one-dimensional case with the scalar values. We can expand this easily to multivariate Gaussian distribution in a vector value space. That's why we have those x's in vector format. So in this case, when you have multiple of those in higher dimensional space, we can have mu in vector space as well. And also, since we are having multiple variances, we need to refer it to covariance. And that's why we have covariance. So it just, the name resembles its own function, right? It's a variance between several variances. That's why we call it covariance. So suppose if you slice this model from this direction, right? You slice it like this. So you're going to end up with a contour data. You're going to have a bunch of data here and some outside, right? So it's going to be in 2D. This is 3D. And you're going to have two features, x1 and x2 here. Okay, so similar for the univariate case, a multivariate Gaussian model can be defined as another normal function with the x and these two parameters. Thus, this represents a true probability pi of x given this. So if we for a given data x, if we find the mean and covariance, so we can showcase this distribution using a normal distribution. Okay, and this one, just like before, you're going to have again a normalizing constant. So this has been raised to d divided by 2 is as if you do the square root, right? And then this covariance, this normalizing covariance, so this value actually represents the determinant of the covariance matrix. And just like before, you have a quadratic function of exponential. So note this minus here. So let's talk about each of these. So you have the vector of x minus the vector of mu's transpose, and the covariance of I inverse, and then you're going to have again the vector of x minus the mu. So these three are having different shapes, but they're in a way that we can multiply them, right, using matrix multiplication. So the first one has a row vector. This is a row vector matrix. This one is a square shape, so d by d. And this one is obviously column. All right. So can anyone tell me if you multiply a row d with d by d and a column vector of d, what's going to be the result?
Scale.
That's right. And that's why we have a probability here, right? That's going to be the p-value. All right. Just like the univariate version, we can have, so this is a real mean, we can compute the mean and covariance. And these are the estimates of the mean and covariance. For the estimate mean of the multivariate, we mentioned it with E or another vector here like this. Sometimes people representing like this. But yeah. Anyways, so we call it expected value, and this is equal to the estimate of the mean. And also we can compute the covariance between features. In this case, we have two features. This way, x minus the mean multiplied by x minus mean transpose, right? So these are in vector space. All right. So, and then we talk about how we're going to be able to estimate a bomb-shaped function or a bell-shaped function using Gaussian models. So we defined, given our data set D, we were interested in finding these parameters for all the j's from 1 to k. So these were the number of bumps. Number of bumps we had was up to k. And that was the weighted, weight we were assigning to each bump. So the final integral becomes 1, right? So integral of px dx becomes 1. This helps because at the end of the day, all of these, all the summation of w's was 1. So assigning this, multiplying this to the probability we were estimating helps this one becomes 1. Because it's going to weight each of those bumps in a way that the summation of all becomes 1, right? And then we were interested in maximizing this probability for all of the x's. Thus, we change it to a minimization problem, and we define, just like before, the in-sample error En of our parameters, which was a summation of all minus log of your w, which I define here, and the probability that this Gaussian model brings. And that was your En of omega, right? So just like before, we transform the problem in a way that we can optimize this formula and come up with the best bell-shaped function given certain data that we don't have any label for those. So we also define that all the W's should be plus, because if they are minus, we don't have any bumps. And then the summation would be equal to 1, and all the J's, the summation of J's should be a positive number, right? And then we say, because this function is complex, the stochastic gradient descent won't be efficient in this way. That's why there's another iterative algorithm called exploitation maximization, or EM, that can iteratively brings us the best number of clusters or best number of bumps for our data. We talked about the hard decision, and today we're going to talk about the soft decision. So first one, the hard decision one, was the case that these clusters do not overlap each other, right? So we would initialize with arbitrary bump membership. So by bump membership, you're talking about fitting using that joint distribution, if you recall. Let me see, what did I... Yeah. Using that map, if you recall, using the map rule and Bayes theorem, the joint probability distribution, if you recall, given J's, if you recall. So given certain points, they would assign, like for instance, in this case, this point to this bump, right? And we call it bump membership. So we would start with some arbitrary bump membership for our data, for each of the xn's. And then, if you recall, we were having two subproblems, subproblem 1 and 2. It's just think about it as a chicken and egg problem, right? So first you have to start with some arbitrary bump membership, and then for those arbitrary bump membership, you're going to estimate their parameters, W, mean, and covariance, right? And then after you estimated that, again, you're going to estimate a new bump membership using your new estimates, right? And this can carry on and on and on until convergence, right? You have to repeat the step 2 and 3 until convergence. So it's as if you start, you have 3 and 2 here. So you start with like arbitrary 1, and then you estimate the omega here, and then you come up with a new bump membership given the new omega here. So you have these 3 and 2, so these are fitting better now. And then again you carry on in this loop up until this becomes maybe something like this. So this has 3, has higher one, lower one, and the overall summation is equal to 1, right? So that would be a hard case, because in this case, our clusters do not overlap. There is another version of an extension of this, which is called soft version, and we allow the clusters to overlap each other so that this one comes on top of this, so they're not disjoint anymore. The other thing they refer to the algorithm is by their name. So this E stands for exploitation, M stands for maximization. So each of the steps are doing one of these. So one step we do exploitation, one step we do maximization, right? That's why we call it EM. E step or M step. All right, so I mentioned about the difference between soft and hard. So hard at each step, xn belongs to only one of the b's, one of the bumps. But soft at each step, the fraction of xn belonging to bj in iteration t. So we have to find a parameter to define this. At iteration t, so we need to take into account the iteration t, bump j and xn, that's why we call it an omega n of j that takes into account all these three, right? So we're going to use it in the soft decision algorithm. All right, so let's talk about soft decision. At step number 1, so we already defined that the fraction of xn belonging to bj in iteration t, we define it by omega n of j at t. So at this iteration t, we have some properties for that. Of course, this one is a positive point, and also the summation of all should be 1, obviously, because the summation of all xn's belonging to all the bj's at all the iterations, at each iteration should be 1. Otherwise, we're gonna use a data twice, right? So the task here is to update the omega, the w's, the mu's, and covariances. Given this, given the fraction of each xn belonging to bj at iteration t, right? All right, step 2, when we have, now we need to define another parameter that can hold the summation of this at each iteration, right? Nj. So this Nj used to be n for the previous case, right? But since we are doing it iteratively and some fractions could overlap with the others, so we have to define a new Nj. That's why we have to define a new W given the new Nj's, right? So this Wj of t is going to be normalizing, will normalize the height of the bumps at each of the j's up to 1 to k, which was the number of bumps. So now given the new wj and the nj, we can define the new vector format of mu or mean, which in this case will be 1 divided by njt and the summation of all those, right? So the x's and the fraction of x's belonging to bj at iteration x. So we need to do the mean this way now, because at some point some of the x's are here, right, instead of being there. So you need to take this into account as well, using this. The same thing goes with the covariances. So this is xn minus mu j of t, and this one is transpose, so you're talking about a vector space. You have to multiply it again by lambda, the gamma n of j at iteration t, and you're going to divide it by njt. Right? Now this will give you the estimation of your mu and your covariance. So the whole step 2 is estimating the parameter, right? All the parameters of the normal distribution. So now we go to step 3, and now we have to update this given that estimate of omega, right? So given the one that we calculated at step 2, this comes from, yeah.
Sorry, can you go back real quick?
Yeah.
The very last line, is that xn?
Yeah, xn minus mu j of t, so yeah, just like this, and transpose. Yeah, I don't know why it just got, yeah, this is like this. Yeah. All right, now this one came from step 2, your parameters. Okay. And now given this, you have to update this, right? So how are we going to update this? The same map rule that we got to know last lecture, Bayes theorem. So the probability of cluster J given xn. So we want to compute the likelihood of a bulk membership given xn. So this will be equal to the probability of xn given being in cluster J multiplied by the probability of that cluster itself, the cluster J, and divided by the total probability. So the overall Px. And we show that this will be equal to the multiplication of your W's by the probability that this normal distribution given these hyperparameters bring. I mean, sometimes you might see it, the W after this, but I mean, both two cases would be equal because this is like a simple multiplication. So the first one is equal to this, and second one is the summation of all, right? All right, now that we can compute, now we can update the omega n of j. It's as if we can update the new membership, the new fraction of membership given those x's, right? And again we can compute this up to convergence. So if you want to define soft decision in a pseudocode way, so we have the first step to initialize, and then second, given the omega n and j at t, we're going to update the parameters, and then given the updated parameters, we update again the new omega. So this is actually referring to time t plus 1, if you want to be super accurate. So this is at t plus 1. Again, at t plus 1, we're going to do this, and then t plus 2 becomes here. So we repeat 2 and 3 up to convergence. So when we see that the changes in parameters are very small, so it's sort of, we found ourselves in a saturated situation. Question?
Is that we update the omega, then at the third step we use the new omega?
That's right. Yeah, this is a new omega. That came from number 2. That's why it's an egg and chicken problem. So you have to start with this and come with that. Again, iteratively you go loop over this. That's why we have to initialize something random first to start with. All right, so we're almost done. I'm just going to showcase some iterations of a real EM in soft decision version. So these are come from a professor in University of California at Irvine, so Professor Smith. So you don't have to write it down because they're in the slides. And so this is the first step. We have a bunch of data. We don't know the labels, right? We don't know the source. What we could do is we estimate 2 features. So red blood cell volume based on their volume, and also red blood cell concentration. So these 2 features, which was a thing we could do, and we have no idea what's going to happen here. Can anyone estimate what's going to be the 2 clusters here? Just looking at this shape.
Probably the top right one.
Yeah?
Maybe some around the center, I guess.
That's right, yeah. It's a good rough estimation. So you could see that the distribution here of the data, they're sort of matching and they're together. So probably we need something here and maybe something for the rest. All right, let's see in several iterations what can EM bring. So these are the arbitrary starting point. So we have 2 clusters. They can overlap because it's soft version. And then we estimate the new lambda, the new omega for this, and then the new bump membership. So another iteration. So this is iteration number 3 actually. So again, it goes up to iteration number 5. It finds a bigger cluster for the red one so that it can encompass these points as well. And the green one is keeps shrinking, right? At iteration number 10, the green one is going towards the one we thought, towards this distribution here. And the red one tries to bring the rest inside. Iteration number 15, 25, right? And then after that, we saw that the changes are very minimal. So we see that it is a saturated point. So In this case, the algorithm converges. No matter how many more iterations we go, the changes are very minimal. And one of the other things you can use in order to understand if you have been saturated is when you plot the log likelihood, at this point you see at iteration around 15, you don't gain that much here. So after here, so already you are saturated. So iteration 16 to 25, we're almost the same. So yeah, so that's basically the mechanics of the algorithm. You can play around with your, maybe a new tutorial we have, or yeah, in a tutorial session you're gonna see more examples on this. But again, in MATLAB or Python, you have these libraries available. You can just play around with your data as well. All right, so the density estimation is over, and next section would be VC dimension and pack learning. So we're gonna be doing that for a few weeks, and then we conclude the course with SVMs. Any questions? All right.
You know anything about the midterm marks?
I haven't received the marks. The TAs are still correcting them. They're gonna let us know maybe tomorrow, and then we update in Kirkus maybe Sunday night or Monday. Yeah, but no worries, you're gonna be fine. All right, see you guys on Monday.